Hi everyone, I'm Sam, and today we're going to be going through Lab 3 for fluid mechanics. So for part 1 of Lab 3, we're going to be using the rectangular flume. So we're going to use some different methods of measuring flow, one of which is going to be the rectangular weir. This is the equation here that describes the rectangular weir flow. So that is, our flow over the weir is equal to 2/3 of a coefficient times the square root of 2 times acceleration due to gravity times the height relative to the height of the water relative to the weir raised to 3/2 times the length of the weir. So for any given rectangular weir, that can be simplified to Q equals A H to the N. N here is our 3/2, and H is still H. A is all of this here, and the length of the weir. You're going to be fitting your data that you collect from this lab to that equation. So also, we're going to be using continuity to describe flow. So for any given body of water in which the volume is not changing, the flow is going to be equal to the velocity times the cross-sectional area perpendicular to that velocity. So over here, we have our rectangular flume. The flow is going to come down from the piping in the ceiling, come down into our tank here, and it's going to flow through our rectangular flume. Alright, so our rectangular flume here is controlled by the pump box over here, where we adjust the percent power delivered to the pump. We're going to start at 51% and go down in increments of 3%. This here is our ultrasonic flow meter. This is going to measure the velocity over here in this figure, and then using the velocity and the 3.75-inch diameter of the piping, you'll be able to calculate the flow traveling through the piping in the ceiling. Our second method of measuring flow is going to be the Marsh-McBurney flow meter. The Marsh-McBurney flow meter is set so that it is 4/10 of the depth of the flow from the bottom, or 6/10 from the top. The Marsh-McBurney flow meter is going to measure the velocity, it'll be right here once the water is flowing. You'll be able to calculate the flow using the depth of flow, which will be observed by holding the ruler up to the water or the flume and measuring the depth. And you'll be able to get your width by measuring across, and it is a 10-inch flume. So that's going to be your width for all the trials. The next way we're going to be measuring the flow is via our sharp crested weir. So we have our sharp crested weir here, and using the weir equation I discussed earlier, we'll be able to calculate flow using the height that we'll find with the hook gauge. With the hook gauge, you can see this number changes here based on where the hook's sitting. So when we are running the trial, we're going to have it so that the top of the hook there will be sitting just level with the water surface. At the end of all the trials, when we have the water sitting stationary in the flume level with the top of the weir, we'll get an additional hook gauge measurement, so that we'll know the height of the hook gauge when there's no flow and no height relative to the weir. For our last way of measuring the flow, we're going to be using the weigh tank here. When we're running the trials, the water is going to be sitting at a level within the tank. Essentially what we're going to do is we're going to use the valve down there in order to stop the water from flowing out of the tank. We're going to shut the valve, closing off the bottom of the tank, and we're going to wait until the tank is heavy enough such that the weight here rises. At that point, we're going to be adding a weight which equates to 200 pounds in the 200 pounds in the tank, and we're going to start a stopwatch as soon as this is tripped. At that point, it's going to drop again when we add the weight, and then we're going to wait until the tank is heavy enough so that it displaces those additional 200 pounds and rises again, at which point we'll stop the stopwatch. That'll give us the amount of weight that has been added to the tank and the amount of time over which that has taken place. That will give us a weight flow rate, which using density we can convert to a volumetric flow rate. Density is partially dependent on the temperature. We're going to be recording the temperature, and it's currently 68.5 degrees Fahrenheit in the lab, which you convert into Celsius in order to find the density.
Alrighty. I'm going to start recording.
Yeah, it'll be a minute until it's at full height, so yeah, a second.
I love how it tracks backwards like that.
Yeah, that's cool.
That's really cool.
I think I'll start going the other way.
Yeah, that's awesome.
So we're going to get started on trial number 1. For a trial number 1, the pump is running at 51% capacity. Our velocity in the piping above is 8.69 feet per second. The velocity at the Marsh-McBurney flow meter is fluctuating slightly, but it's about 0.53 feet per second. The depth of the water at the Marsh-McBurney flow meter is 14.25 inches. The hook gauge reads 4.72 inches. And for this trial, we're going to be skipping the flow tank because the resting water surface is too close to the top, so it would overflow if we attempted to do it. So we're going to hold off for a trial or two to do that. Now we're going to do trial 2 of part 1. So for this trial, we have the pump running at 48%. Our velocity is currently 8.03 feet per second in the piping. For the Marsh-McBurney flow meter, the water is moving it's fluctuating at about 0.47 to 0.5, so call it 0.47 feet per second. And the depth of the water is about 14.1 inches. And the hook gauge is reading 4.53 inches. So we're going to do the weight tank for trial 2 now. So what's going to happen is that Roosevelt is going to pull the lever over there, causing the flow to be cut off from the bottom of the tank, causing all the water flowing from the flume to stay in the tank and increase the weight. So we know that if we add, so at this point, the weight over here equates to being more than what's in the tank. At a short time after Roosevelt pulls the lever, the weight of the water in the tank is going to be greater than the weight on the scale, at which point I will start the stopwatch and add the equivalent of 200 pounds to the scale. After that, so we're going to wait until the tank again equals the weight on the scale, at which point we'll know how long it's been, or how long it took for the water flowing from the flume to weigh 200 pounds, and be able to use that to find a mass flow rate, and we can use that to find a volumetric flow rate. So, Roosevelt, whenever you're ready. Alright, we're starting. I'm going to add the 200 pounds. And boom. It was 7.33 seconds to add 200 pounds of weight. Trial 3. The pump is running at 45% power. The velocity in the pipes is 7.24 feet per second. The Marsh-McBurney flow meter is reading about 0.45 feet per second, and the depth in the flume is 13.9 inches. Hook gauge is currently reading 4.35 inches. We're going to be doing the weight tank for trial 3 now. So we're going to be putting on a 200-pound weight. So we're going to be looking for the time it takes for the 200 pounds to be displaced. So Roosevelt, whenever you're ready. So we're starting it?
Yeah.
Okay, so it took 7.97 seconds to displace 200 pounds. So we're now on trial 4 of part 1 of the lab. The pump is running at 42% capacity. The velocity in the pipes is 6.50 feet per second. The Marsh-McBurney flow meter is reading approximately 0.41, or it just dropped, so call it 0.40 feet per second, so 0.40, with a depth of, we'll call that 13.7 inches. The hook gauge is currently reading 4.09 inches. Alright, we're now going to do the weight tank for trial number 3.
Yes. No, 4.
For shot number 4, sorry. So we're using 200 pounds. So Rose Bay, whenever you're ready.
Yeah.
All right. All right. It was 8.70 seconds. All right, we're now on trial number 5, part 1 of lab 3. The pump is currently running at 39% power. The velocity in the pipes is 5.63 feet per second. The Marsh-McBurney flow meter is currently reading 0.34 feet per second at a depth of approximately 13.4 inches. The hook gauge is currently reading 3.82 inches. Now we're going to do the weight count exercise. We're using 200 pounds again. So Rose Bay, whenever you're ready.
Yeah.
We're starting. And we're good. It's 10.08 seconds. Alright, we're now on trial 6 of part 1 of lap 3. The pump is running at 36% power. The water in the pipes is flowing at 4.75 feet per second. The Marsh-McBurney flow meter is currently reading 0.28 feet per second, or just jumped up. Call it 0.3 feet per second. It does fluctuate. At a depth of approximately 13.2 inches. The hook gauge is reading 3.56 inches. So we're now going to do a wave tank. Rose Bay, whenever you're ready. Reads 11.96 seconds. Alright, so we are now on trial 7 of part 2 of lab 3. Our pump is currently running at 33% power. The water is flowing at 3.80 feet per second in the ceiling pipes. The Marsh-McBurney flow meter currently reading 0.22 feet per second. Take your input. At a depth of 12.75 inches. The hook gauge currently reading 3.21 feet. inches, 3.21 inches. All right, we're gonna do the weight tank with 200 pounds again. So Rose Bay, whenever you're ready. All right. That was 14.89 seconds. We're now going to take our zero reading on the hook gauge. So as you can see here, the water has ceased to flow through the flume and is now simply sitting level with the top of the weir. So this gives us the height of the weir on the hook gauge. So it is currently reading 1.26 inches. So you're going to take that number, you're going to subtract it from all of your hook gauge readings on trials 1 through 7 to get the height of the water relative to the weir. So that's it for part 1, and now we can move on to part 2. So we're going to move into part 2 of lab 3 now, which is going to be using a Venturi meter. So the equation we're going to be using for the most part is our Venturi equation here. The equation here is that the flow through the Venturi is equal to the Venturi coefficient multiplied by the area of the throat of the Venturi, which is the narrow part of the Venturi at the center, multiplied by the square root of 2 times the acceleration due to gravity times the deflection in the Venturi manometers, which we'll get into when I get over to the apparatus. And it's all going to be divided by the top part divided by the square root of 1 minus the ratio of the Venturi diameters of the wide part and the short part, or narrow part, raised to the 4th power. So our ratio here is the diameter of the Venturi throat divided by the diameter of the wide part of the Venturi. This here is our tilting flume. We have currently set up a Venturi meter set up in the Venturi. We have the manometer at the throat of Venturi and the wide section of the Venturi. These are going to cause the water level to rise up into the Venturi manometer, and we're going to measure the height of that water level from the top of the tube for each of these, and the difference between those is going to be our deflection. So in this case we have a valve here at the end so that we can block off the end of the part of the flow so that we maintain full pressurized flow in the Venturi and have no open channel flow taking place. When we're running this, our water is going to back up behind this here wall, and for each trial we're going to keep a consistent level of water within that trial. We're going to be starting at 13 inches and going down in increments of 1/2 inch. Over here, we have our pump. We can move over here. Yeah. So we have our pump and the pump manometers. We're going to be using pump 1 in this experiment, and these are our pump manometers. These are going to read the height of the the velocity of the water coming through the pump orifices. So there's a large orifice, a small orifice, which are essentially the valves that the water flows through from the pump into our tank. So the deflection of the manometers is going to be read by reading the difference in the level of these two columns of water. So if these 2 columns of water settle 1 foot apart, our deflection would be 1 foot. If they settle 1/2 foot apart, our deflection would be 1/2 foot. We're going to be using those figures and looking at them on this figure here, which we have on the y-axis a logarithmic deflection thing. So if they're 1/2 foot, we would follow the 1/2 foot deflection over to the small orifice curve, and we follow that down to our logarithmic flow axis. So for example, 1/2 foot would be approximately 0.05 cubic feet per second. So that's how we get our flow for the data sheet. We're also going to be recording the water height for data also.
Step one is just this, right? Step two is all
So we are currently at 13 inches of water depth. Our deflection over here on the orifice is currently sitting at 2.07 and 2.15. So our deflection is 0.08 feet. Reesbag, you want to get the deflection over there? So
First one, look at 725, 7.25 inches, and for the second one, it's 4.75.
So for trial one, our manometer deflection was 0.08 feet. So we find that here on this line, right here. You run your finger along the line to the large orifice line, and you read the number right off, and it's exactly 0.06 CFS.
So our water level currently sits at 12.5 inches.
Here on the manometers, manometer 1 is 2.5, 2.7, and 2.1 flat.
2.7, 2.15.
And for here we have 6.75.
6.7, oh,
One second.
6.75?
Yep.
Yeah. And here 5.4. 5.4.
5.4. So for trial one, our manometer deflection was 0.08 feet. So we find that here on this line, right here. You run your finger along the line to the large orifice line, and you read the number right off, and it's exactly 0.06 CFS.
Yeah, water level is currently at 12 inches.
And then on the manometer, we have about 2.065 and 2.15.
And here we have 6.25. And
0.5.
here 5.3.
5.3. Okay. So for trial one, our manometer deflection was 0.08 feet. So we find that here on this line, right here. You run your finger along the line to the large orifice line, and you read the number right off, and it's exactly 0.06 CFS.
This is trial four, and the water level is currently at 11.5 inches.
So then when we look at the manometers, we have about 2.072 and 2.15 again.
ready, Casti?
Yes. So,
yeah. No
so
problem.
here we have 5.55.
5.55.
And for the lower one, we have 4.75.
4.7.
So for trial 1, our manometer deflection was 0.08 feet. So we find that here on this line, right here. You run your finger along the line to the large orifice line, and you read the number right off, and it's exactly 0.06 CFS.
Alright, the water level currently sits at 11 inches for a trial 5.
So looking at the manometers, we have about 2.08 and 2.14.
So here we have 5.25. And for the other one, we have 4.4.
So for trial 1, our manometer deflection was 0.08 feet. So we find that here on this line, right here. You run your finger along the line to the large orifice line, and you read the number right off, and it's exactly 0.06 CFS.
So the water level is 10.5 inches.
Trial 6.
So looking at the manometer, we have 2.08 for 1 and 2.14 for 2.
So here, the level is 4.55.
4.55?
And here it is exactly 4.00.
4.2.
Yep. So for trial 1, our manometer deflection was 0.08 feet. So we find that here on this line, right here. You run your finger along the line to the large orifice line, and you read the number right off, and it's exactly 0.06 CFS.
This is trial 7. The water level is at 10 inches.
When we look here at the manometers, we have about 2.075 and 2.145.
Here we have 4.10.
12.10.
And on the other side we have 3.55.
3.55.
So for trial 1, our manometer deflection was 0.08 feet. So we find that here on this line, right here. You run your finger along the line to the large orifice line, and you read the number right off, and it's exactly 0.06 CFS.